Welcome back to our series on modeling, in which we are trying to make a basic climate model for an Earth-like planet. On our last episode, we made the planet with no atmosphere and found it was a frozen world at 255 Kelvin, negative 18 Celsius. This time we're going to add an atmosphere and see if we can get the temperature tuned to our measured average global temperature of 15 degrees Celsius, or about 288.15 Kelvin. Now, before launching into this model, we should consider how various kinds of bodies absorb and release radiative energy. This is the model we ended with last time, and I want to take a little bit closer look at the equation over here, which was surface area times Stefan-Boltzmann constant times temperature to the fourth power. The formula given here is for a black body, which is a hypothetical body that absorbs all radiant energy hitting it and emits along a continuum of wavelengths at the maximum rate for its temperature. Like I said, it's hypothetical and doesn't exist. Even a black hole isn't a true black body. But both the Sun and Earth are close enough approximations to black bodies that I simplified our model last time and had the radiation coming off the Earth be a just black body equation. Gustav Kirchhoff showed that the intensity of radiation is equal to the Stefan-Boltzmann constant times the temperature to the fourth power. Now, this equation has units of watts per square meter, and for our last model we multiplied by surface area to get the total watts radiating from our model's Earth reservoir. I'll stick with the watts per square meter form over here for this part of the discussion. To build an atmosphere into our model, start by looking around you. Look around and see how the air definitely does not absorb all the radiation that hits it. Otherwise, you couldn't see anything. The atmosphere does not absorb visible radiation, hardly at all, but it does absorb longer thermal IR, infrared, somewhat like a pane of glass that lets visible light through but inhibits thermal infrared passage back out. Gustav Kirchhoff, who coined the term blackbody radiation in his doctoral thesis in 1860, also pointed out that such radiation should be emitted in a continuum of wavelengths with the total energy in watts per square meters given by our equation. But the flavor of that EMR is important as well. It was the greatest name in all of science, Wilhelm Karl Werner Otto Fritz Franz Wien, who pointed out that the wavelength of maximum emission is inversely proportional to the temperature of the body, and fortunately it is only known as Viens Law and is simply wavelength in micrometers is equal to 2,900 over the temperature in Kelvin. So we see here that the surface temperature of the Sun at about 6,000 Kelvin has its maximum output in the visible. The Earth has an average surface temperature of 15 C, or 288.15 Kelvin, and at that temperature the maximum wavelength of light is in the longer thermal IR. Now let's take a look at the greenhouse effect simulator from our sister school at the University of Colorado in Boulder. If you go to your favorite web browser and just search for greenhouse gas simulator, this greenhouse effect PHET University of Colorado Boulder should come up, and when you go there you can download it or run it. I've already downloaded it, so we'll take a look over here at initially the glass layers model they have, in which you can take a look at the solar output, which is maximally in the visible, as we said, so they're representing those with yellow little dots of photons coming down that gets absorbed into the surface of the Earth. The Earth heats to 15 degrees Celsius, or 288.15 Kelvin. And in this model we have actually no atmosphere, so it's like our model. Hey, 255 Kelvin, negative 19 Celsius in this case. So this is no greenhouse effect at all. I'll speed this up here so we can see a little bit more of the action, huh? In fact, you can see all the photons. Ooh, that's really good. Now we can start putting in panes of glass. Put in one pane of glass and you start to get a moderate effect. Maybe we shouldn't view all photons. It's easier to see that we're starting to let some of those infrared photons through, but not all of them. Some of them get absorbed, bounce back down towards the surface, and now the surface temperature is starting to go up from that 255 Kelvin to near 300 Kelvin, or 25 degrees Celsius. We can put in another pane of glass. Okay, the temperature is going to go up again, but not as much. So a second equal pane of glass is not equal in its absorptive ability as you put one stacked on top of another. You do get the temperature increase with each one, but not quite as much. Now this is due to the well, this is an analogy for our greenhouse effect. If we go over to look at it on a molecular level, we can see they've given us a gun here to shoot visible photons at things like nitrogen, N2, which is 78% of the atmosphere by volume, and you see it just goes right through. Oxygen, 21%, just goes right through. Okay, let's do the math. 78 plus 21 is 99% of the volume of the atmosphere, lets this pass through. But what about the other gases? Oh, they let it pass through too. Yep. Visible light just passes through our atmosphere in general. The major constituents over here and the minor constituents over here. So go back to the nitrogen and let's start shooting infrared photons at it and see if that will absorb. Nope. 78% of the volume of the atmosphere does not absorb. How about oxygen? 21%? Nope. 99% of the atmosphere does not interact with thermal infrared photons. They also, these two, have two atoms in them. The next most abundant permanent gas in the atmosphere is argon, and it's just one atom. It doesn't interact with these photons either. Now get up to 3 atoms in the structure, not everything, but okay, water will absorb and start throwing these, absorbing this, goes into kinetic energy, and then throws an infrared photon out in some random direction, which statistically means half of them gets thrown out away from the gun and half of them get thrown back towards the gun. All right? So water does it. CO2 does it. So this is the greenhouse gas that most people talk about, you know, the CO2 molecules, but we'll bring water into this as well next time. And methane over here with a total of 5 atoms, and it will also resonate with these thermal IR photons and then re-emit in random directions, half up and half down. So we can build up an atmosphere here and say, all right, shoot a bunch of infrared photons coming out of the gun, start to try to block with nitrogen. Well, that doesn't seem to do anything. Oxygen. Well, that's most of the atmosphere there. It just doesn't interact with this stuff. So when the Earth is at 15 C, 288.15 Kelvin, it's just spitting out these thermal IR photons, and the major constituents of the atmosphere don't do a thing. But you put a little bit of water in there. Oop, hey, we threw one back towards the gun. Let's put a little bit of carbon dioxide in there. Let's put a little bit of methane in there. It doesn't take much. We've now made a greenhouse effect. This is a very small greenhouse effect, of course. If we wanted to have a little bit more pronounced greenhouse effect, maybe we take it up to the medium levels here. All right. And so we can take away the major constituents, clean this up completely because it's really doing nothing. It's these minor constituents that are doing all of the greenhouse effect. Now we can put that together with their overall model and say, okay, we have the visible photons coming down, absorbing in the surface, and then re-radiating to space, and we have no greenhouse effect, and so we're at 255 Kelvin. That was our model with no atmosphere last time. We came to the same answer. We could play around with this one and say, well, what if we boosted the greenhouse effect a little bit? Well, in that case, every once in a while you see one of these photons bounce back down, and that's going to keep the temperature a little bit higher. We can even take it up to set times that they have, the Ice Age. Alright, at the Ice Age it was a frozen world, but not a tremendously frozen world. We still had life on it, and so our atmosphere in this case seems to come up to a temperature of about, freezing, near 33 degrees Fahrenheit, 1 or 2, 3 degrees Celsius. Take it up to pre-industrial. Alright, we're in the pre-industrial age, and we have a greenhouse effect that it's rather moderate and took us up to about 9-10 degrees Celsius, 285, 86 degrees, Kelvin. And then we go up to today. Hey, we got a satellite. And there you go. We've got coming up to the 288.15 Kelvin. We can throw some clouds in here too if you want. Makes it rather pretty. Now clouds are of course the nightmare in modeling. They're the thing we understand the least about, but we're getting a better hold on those guys. Alright, now with that in place, come back over here. Having viewed that, you realize the atmosphere is not a perfect black body because it only absorbs some of the energy that hits it and only emits at a discrete wavelengths. And for such a case, we call it a gray body. Mathematically, going from a black body to a gray body is rather simple. We just say what fraction of the radiation is emitted from the gray body compared to a black body. We use the same equation as before, but add in epsilon, a fractional constant that varies from 0 for a perfect reflector or white body to 1 for a perfect absorber and emitter or a black body. Since there is no such thing as a black body, every object has its own value of epsilon, and we call it the emissivity of an object. Most objects have an emissivity over 0.9, but air is a bit lower, low enough that we can't approximate it as a black body. Like the Earth energy reservoir, the atmosphere will hold joules of energy and radiate it out, but using this equation. So the atmosphere radiation is different from the Earth surface radiation in that you reduce it by its emissivity. But there's another difference, which is that the Earth's surface can only radiate up into the atmosphere or through the atmosphere to space. The atmosphere can radiate in all directions statistically, right? It's not forced to just go up. So when you statistically radiate in all directions, half of it goes up to space and half of it will come back down to the Earth, and that is the greenhouse effect. So we're going to have to model that. But how much energy goes into the atmosphere versus going into space to start with? Well, that's due to what we call absorptivity of the atmosphere, not the emissivity. The absorptivity, like emissivity, is a unitless fraction from 0 to 1 saying what percentage of radiation does our body absorb when it's hit. A great convenience for our model will be the corollary of Kirchhoff's law that a body at thermal equilibrium will have its absorptivity equal its emissivity. So let's get to building our model. We don't have to completely start from scratch. We can start with our model with no atmosphere from before. But this energy out of the atmosphere, I'm going to have to split one part out to space, right? So I'll go ahead and do that. Say I have to take one part out to space. So I'll call that IR to space. It won't be fancy, just space. All right. And I already know I'm going to have to clunk up this side, so let's start cleaning up. Some things I could do real quick to note. Our solar in is just going to be the same as before, cross-section 1 minus the albedo, which is set to 0.3, and the solar constant that I have is set to 1361. If you're using a different number, watch out, I'm going to come out with different values. Alright, so cross-section of the little area is using the radius in meters, pi r squared, and our surface area is 4 times that. The temperature of our atmosphere before was Earth energy divided by its heat capacity, and now we're going to have to flux some of the energy out to space and some into an atmospheric reservoir. And I cannot just take a reservoir here and try to slap it onto one of these endpoints. It won't let me do that, so get rid of that. And I'm going to have to blow this whole thing up. I know it hurts, doesn't it? You made this, it was such a struggle. But hey, you know what? It's easy to repeat. We can just Control, copy this particular equation here, and we're going to paste it into a variable over on this side. But you can't just paste any equation in. You got to connect everything that you need together. Now, surface radiation I'm going to need for my IR to space and my IR to the atmosphere. So this, I'm just going to call this surface radiation. So SR for surface radiation. And it has the equation of surface area times the Stefan-Boltzmann constant, which I really don't need over there anymore. So why don't I just swing it around over here? Yeah, I can do that. bring you down here. Makes you a little easier to deal with. And add that in. And then we also need the temperature. That's a little hard to just drag around. I'm going to go ahead and try a ghost on that one. The temperature over here, I'm going to snuggle everything in as much as I can to start with and move it around to keep it neat when I need to. So the temperature of the Earth, in this case, going out of this radiation. Now we can define it, which is easy as Control-V, paste. Hey, alright, and return, and hey, it's defined. We're good. Now that was the radiation that came out to space before. All of it dumped to space when we had no atmosphere. But now we're saying some goes to space, some goes to an atmosphere. So goodbye, Control, click, delete. It's gone. Because I need to make an atmospheric energy component. And we're going to have some of the energy from the Earth go to space, but the rest of it go to this atmospheric energy component over here. So IR to atmosphere. Alright, now we're going to define how this radiates out. We know that it's the surface radiation that's dumping out. Surface radiation is dumping out, but we can't do this twice because we'll double the amount of radiation coming out of the system at the moment if I just dump as surface radiation out of both of these. So it's a percentage. What percent goes into the atmosphere? What percent goes to space? We said that that was a function of something we call the atmospheric absorption coefficient. So I'm going to need an atmospheric absorption coefficient, which we said is a variable parameter that is going to have to vary, be a fractionator from 0. And I like to use lots of decimals, and sometimes it sticks you into integers over here, and if it does that to you, just type out 0, 0. I want at least that many decimal places, 0.000. Oops, we're going from 0 to 1. Think about it. And then we're going to set an initial parameter. I don't know what the atmospheric absorption coefficient is. I do know that the average surface temperature of the Earth is 15 C, or 288.15 Kelvin. So I can start playing with this parameter later, but for now let's just put it at 0.5 in the middle, because I don't know what it is. We'll see if I'm high or low when I set it there. Alright, that atmospheric absorption coefficient is going to have to feed into what goes to space, because some percentage is going to go out to space, and then what percentage of it goes into the atmosphere. The atmospheric absorption coefficient is the percentage that goes into the atmosphere. So to define this into the atmosphere over here, it's the surface radiation, but not all of it. It's the percentage that is absorbed by the atmosphere. There we go, easy enough. The IR to space then is the rest. So the surface radiation times what does not get absorbed by the atmosphere, which in mathematical terms we write as 1 minus the atmospheric absorption coefficient. The rest goes to space. Alright, now we're going to start dumping joules of energy that start at 0 in here. Don't worry, just like the Earth that started at 0, it added up joules and then started radiating out. Initially with a temperature of 0 Kelvin, you won't radiate anything, and so it has to get up to that equilibrium point. So it starts at 0 over here, and it's going to radiate out by a temperature, but not the Earth's temperature. It's the atmosphere's temperature. The Earth's temperature was Earth energy divided by the heat capacity of the Earth. Well, this is going to be similar. I need an atmospheric temperature, and it is going to be a function of the energy in the atmospheric reservoir divided by the heat capacity of the atmosphere. Okay, I gave you a lot of parameters to fill in over here to get your heat capacity of the Earth system. I'm going to make it easier for you over here. I'll give you 2 basic parameters of the atmosphere that shall do the trick for us, which are the mass of the atmosphere and the specific heat of the atmosphere. So we know that it's atmospheric energy divided by heat capacity. Alright, heat capacity is always in joules over Kelvin. I just gave you mass of the atmosphere. Kilograms is not in there. Okay, here's the mass is 5.14 times 10 to the 18th kilograms. Now, if we take specific heat, as I said, it's 1004 joules over kilograms times Kelvin. Now, look at what you can do. You multiply those two units together, and you end up with joules over Kelvin, which are the units of heat capacity. So all I need to do here is atmospheric energy divided by the mass of the atmosphere, 5.14, times, and we're going to say E times 10 to the 18th, times 1004 joules per over Kelvin kilogram. All right? And that finishes the equation for temperature of the atmosphere. It's a done deal. We did it. Now, it is going to feed into how the atmosphere radiates out. But we said radiates differently than the surface of the Earth because it can statistically radiate half out to space and half back to the surface. And I am going to get some messy diagrams here, so I'll do my best. It doesn't let me move these things very well in this program to clear things up, so it wants to connect like that, putting that one on top. Okay, fine. So this is atmosphere to surface. Ooh, is that messy? So trying to clean up here, atmosphere to surface. I'll stick you in here, drag you out, give you a little bit more room to work with. And I got a little bit of crossing of lines now going across. It's just a sacrifice of the program. We're going to have to get a little cluttered as we get a bit more stuff in here. We have also another flux that goes out to space. And we can just dump that out, and that's atmosphere to space. Okay. And I think I need to define this using the temperature of the atmosphere, right? We're going to use that gray body equation that had temperature to the fourth power still. So yeah, we still have to have the atmospheric temperature in here. But I also had surface area as we had before. So surface area comes in. Oh boy, this is going to get messy. Surface area comes in, as does the Stefan-Boltzmann constant, which got tucked in over here, unfortunately. I think it's best if I just ghost at this point to deal with that Stefan-Boltzmann and say you need to be a variable in each of these equations as well. Boy, are we getting messy. Spaghetti diagram. And the last thing was it doesn't emit all of it. It's got an emissivity. Oh, do I have to put another variable of emissivity here? No, we're in luck because Kirchhoff's corollary law is that the absorptivity is the emissivity when at equilibrium. So we're just going to shortcut that by saying it's the emissivity and connect it to both sides. All right. Not the prettiest ever, but I don't want to waste your time cleaning it up. You can do that on your own time. And now we'll just define out to space. We're going to radiate out of this thing using the same basic equation with the surface area of the Earth, which is, the atmosphere is so thin we can use the surface area of the Earth. This is an approximation model, all right? Times, we'll do the Stefan-Boltzmann constant times, well, this time it's that emissivity, which is equal to our absorption coefficient, which we'll have to play around with, right now set to 0.5, and times the atmospheric temperature to the fourth power. All right. Am I ready to say okay? Not quite. The atmosphere radiates different than the surface of the Earth. Statistically, half of it goes up to space. The other half comes back down to the surface of the Earth. So multiply by 0.5. And before I close out, I'm going to grab all this, copy it. Okay. And that's because I just want to paste it right over here. It's the exact same thing. I don't even have to go in the equation box. Just boom and return, and I'm done. That's how easy that is. The atmosphere takes half of this energy and radiates it out to space. It's the surface area, Stefan Boltzmann, emissivity times the atmospheric temperature to the fourth power times 0.5 or divided by 2, however you want to do it, right? And it's the identical in both, but do not try to take an influencer, make one equation, and then just link over to the other one and say that's the same going out, because that becomes a time step differential that causes a problem. Your energy reservoir wants to radiate equally in both directions. That's what it should be doing in the real world. Every time step, an equal dump in both directions. But if you were to set this one to define the one back to Earth, then you will have this off step, in which this makes a calculation, dumps its energy, then it gives its answer over to this one, which makes its calculation and dumps its energy, and you can start to get some weird effects from that. We're in, we're all black, we're ready to run, we bring in some programs. I can map out either the atmospheric temperature or the Earth temperature. In the end, they come to the same result. You can try it out. I'll go ahead and do it for you. Put in a plotter, add a variable, atmospheric temperature, add another variable, and make it just temperature of the Earth. And then over here, what did we want to play with? Not albedo, not solar constant. We're going to leave those as they were. And put in a slider bar for the atmospheric absorption coefficient, which we set to 0.5, and we're not going to play with to start with. We're just going to let this run. Except this will never run long enough. I've got to take this out for, let's see, how many time steps do I want? How about 30 million? Okay, 1, 2, 3. 1, 2, 3. Yeah, that might do it. Might. You just have to play around with these numbers. It says, start current time to 0. That's where you want it to start, so leave that alone. Display every, oh boy, every what? I'm going to guess every 100,000 time steps. Remember, these are seconds. We've been playing all the units in here were in seconds. Joules go to watts as joules per second. So time step, remember, if you can't see it, you can always grab in between here, expand out a bit. Calculate every 10th time step. I'm afraid I might have to do every 10,000th time step, or I'm going to be sitting here all day. So a little bit coarser information on this. I don't need to see all the little details going on, and so I relax the standards here a bit. The run settings are all fine. Leave them alone. In units, because if I start putting in the units, all right, in a professional level model, yes, to check myself, but at this level it may just cause nightmares. So don't worry about the units, Euler method, and everything else is fine. So we are ready to run this thing, and like I said, not quite enough time on this thing. I should have just put in another 0 here and let it go. There, now it's flatlining for sure. And it flatlines at 273.5. I am frozen still. That's Kelvin. And notice the way that your temperature of the Earth comes up first, faster. If I just clear this whole thing and stop and run again, it is at first the temperature of the Earth that comes up. The atmosphere is dragged up by it, but eventually they come to equilibrium with each other and you're good. Alright, so now I do obviously have to pump up my absorptivity. I'm too cold. How much do I have to pump it up? I'll jump up to 0.7 and give that a shot. See if I'm too low, below 288.15, or too high above that. Alright, we're good to go. So come back over here, and we cleared everything to give a run on our longer run, and yeah, we're low. And I really don't need to see the, I don't know, which one do I want to kill? The atmosphere is a bit prettier, so I'll kill the Earth one. Remove that variable. Alright, clear this whole thing. Reset it and say I was too low. I should go to 0.8. Give that one a shot. Come back, run it. Hey, we went over. So clearly, but not much. We're a lot closer on that side, so I'm not going to jump back down to 0.75. I might try a 0.78. yeah, start there, see what we can do. So bear with me as I play around a little bit here. Okay, so I think I was closest at the range of decimals I gave myself. Okay, 0.7814 as the fractional non-unitless. I don't have to say units on that. That's my absorptivity, and my emissivity constant when I'm at equilibrium is about 0.7814. So we did it. We have made a model with a planet that got up to 288.15. Let me just clear it. My value of 7814 gives me just slightly up above there, 288.1512. Not bad. All right, well done. We have done it. And when we come back next time, we're going to see what happens with a little bit of a greenhouse effect in this thing. What do we have to consider to start forcing this model that we have here? Right now it has a certain amount of greenhouse effect. Remember that the greenhouse effect being this portion going back to the Earth. How do we increase that to increase the temperature on the Earth? Well, that's our job next time. So thanks for your time again, and enjoy your modeling. Take care.